The next talk is by Chiara di Modica. It's about online forecast reconciliation in wind power prediction. Yeah, Chiara, you're on the video. You can share your screen. Chiara, she sent me a very short bio. Chiara, she studied energy engineering in Bologna, and then she actually came to the EU also to study sustainable energy engineering. And yeah, she got an education towards more data and operation research since then. And now she's a research assistant at DTU. Chiara, can you share your screen, or you don't manage to share your screen? Okay.
Yes, I was having some problems. Just 1 second.
So yeah, sure. But Chiara, the floor is yours now.
Yeah, thank you, Pierre. Thank you for being here, everybody, and for having me here. Okay. Well. Today I'm gonna talk about our work on online forecast reconciliation in wind power prediction. And this work builds in the context of renewable power forecasting, which is moving more and more towards a high dimensional setup. So this is because large data collections become available at different levels of spatial and temporal aggregations. And this allows the forecaster to improve forecast quality by accounting for spatial-temporal dependencies existing in the data. But at the same time, the decision maker also needs to make decisions at different levels. So for example, the wind power producers need to bid in the day-ahead market, while the system operator needs to know in advance what is going to be the production at the country level to book enough reserve power. And the decisions at all these levels of aggregation need to be consistent across the hierarchy. So forecast reconciliation basically allows both the forecast to get a higher value in decision making, but also to have higher quality due to the accounting for these spatio-temporal dependencies I was talking about. But what is a hierarchy? So in a spatial sense, it can be that one composed, for example, by the total production of Denmark, the production at regional levels, for example, Sealand and Jutland regions of Denmark, and the individual productions of the wind farms in Denmark. Mathematically, if we look at this hierarchy here on the left, which is composed by 8 nodes, 1 at the top, 2 at the middle, and 5 at the bottom level, this can be uniquely identified by a so-called summing matrix, which allows to compute the sums according to this specific hierarchy structure. And so, for example, if we multiply this matrix by a vector containing a 5-dimensional vector containing the bottom node forecasts at time t, and we then will end up with an 8-dimensional vector containing in the first position the sum of this bottom forecast, at the second position the sum of the first 2, and the third position the sum of the last 3, and the other positions 5 remaining position, the copy-pasted basically bottom forecasts. So basically this allows to this allows us to give the definition of additive coherency. So if we collect the hierarchy information in a vector X, which was basically an 8-dimensional vector in previous example, and the information of the bottom level only is collected in the vector X star, which in that case was a 5-dimensional vector, then the information throughout the hierarchy, so the information in X, is going to be additive coherent if it's equivalent to the information that it would be obtained by aggregating the bottom forecasts. So bottom information. So if X is equal to S times X star. In a hierarchy, observations are naturally additively coherent. So for example, the sum of the individual wind farms productions, it will be equal to the sum of the total production of Denmark. But the corresponding forecasts, which we call base forecasts, if generated independently, will be most likely not additively coherent. So for example, the sum of the forecasts of the bottom forecast will not be equal to the forecast of the sum. And that's where reconciliation becomes the procedure that restores the additive coherence of the base forecasts. There are already methods that do so, and they are all post-processing methods, reconciliation methods that perform linear combination of existing forecasts. Basic methods use information from one level only, while more advanced methods combine actually the information at all nodes and they project it into the aggregate consistency space, onto the space of aggregate consistency. Some of the advanced methods even use historical information of the error covariance structure to actually tweak the direction of that projection. But the limitations of the existing methods is that they do not directly minimize the forecast error, and they do not account for the fact that the underlying processes, including the optimal reconciliation process itself, can be actually non-stationary. So what we propose is to work in a multivariate regression framework and to train and constrain the reconciliation parameters over historical data so that we can minimize the forecast error while reconciling the forecast. The resulting estimator is called MLSC, which stands for multivariate least square equality constraint estimation, and we will call it also batch estimator. And we will extend then this estimator to the online setting deriving the multivariate recursive least square equality constraint estimator, which we'll call also online estimator, which allows us to update those reconciliation parameters that minimize the forecast error over time. I'm not going through the mathematical details of the methods, but I would like to stress what I think are the most important properties of the mentioned estimators, of the proposed estimators. First property is reconciliation by design. So even if only the in-sample-based forecasts are actually constrained to be additively coherent, we have that by construction, both the batch and online estimators actually allow for forecast reconciliation both in sample and out of sample. A second thing we found out is that actually under some conditions, the quality constraint itself is not actually required. So as long as the measurements are themselves additively coherent, by construction, also the MLS and MRLS estimators, which are the same as the batch and online estimators, but without the quality constraint, allow for forecast reconciliation both in sample and out of sample. Now I'm going to show you some results about the performance of the mentioned estimators over real data coming from the Danish wind power dataset provided by Energinet. The dataset is of 2 years of data, 15 minutes resolution data, and we picked 100 wind farms randomly. And then we normalized each series, and we grouped the wind farms in 4 groups, which are visible in this picture, depending on their geographical location. Then the aggregate levels were obtained through the aggregate level series were obtained through sum, ending up with 1 total node, 4 regional nodes, and 100 bottom nodes. For each node, the base forecasts were then obtained training autoregressive models with 2 lags over the first 6 months of the dataset. The last 6 months of the first year of the dataset was then used for training reconciliation methods, which were basically the estimators that we propose, so MRLSC and MLSC, but also a benchmark estimator reconciliation method, which is called MINT. Afterwards, genuine verification was performed over the second year of the dataset. So first results we can look at are the root mean square error and improvement of the root mean square error of the forecast against the base forecast, which are the ones that are not reconciled. So first of all, they are all in percentage. First of all, we can see that the root mean square error is lower for the more aggregate series, which makes sense because they are smoother and therefore easier to forecast. And then if we look at the improvement results, we can see that all reconciliation methods bring improvements, but the largest improvement are brought by the online estimator. Within the online estimator, the largest is then for the less aggregated series, which makes sense because there is the larger room for improvement there. But it's also making sense to look at the distribution of the improvement results among the bottom level. We can still see that on average, the online estimator performs better than the batch estimator, that performs better than the benchmark, but we can see also that the variations of those improvements are much, much higher. Since our assumption is that underlying processes are non-stationary, it's nice to look at the evolution of some of the parameters trained by the online estimators over time. We picked randomly 3 parameters that are the reconciliation or linear combination parameters that we were talking about before. And we see the evolution over time. There are smoother and higher frequency fluctuations, and they show how the tracking basically happens over time. On the same line, we can also look at the results of the improvement of the error over the evaluation period, but on a monthly basis. We can still see that the online estimator is the one that is consistently performing better, and there is also a slight upwards trend. Finally, I would like to show some results regarding a Monte Carlo experiment we made, in which we varied instead of, because the hierarchy structure that we picked up for the previous results, which were basically assigning the wind farms according to the geographical location to the 4 groups, was a pretty specific hierarchy. So then we decided to vary and randomize the assignment process and basically have 100 replicates of this experiment. And these are the results of the improvement, so the distribution of the results of the improvement error. And we can see that the ranking is preserved. The online performs better than the batch, that performs better than the benchmark methods. And there is no variation at the bottom level since it doesn't change across replicates. And a very important result is also not important, but it's kind of interesting to see that now the largest improvement is actually at the regional level instead of at the bottom level. And this is due to the fact that there is a smoothing effect due to the randomization of the assignment process, the group assignment process, which was not there before, as the as basically the differences were enhanced. The group, the geographically dependent assignment process was actually enhancing the differences that are present already in the regions in the data. And to conclude, our approaches basically provide a better use of the available information because they use also the measurements to minimize the forecast error. And then the MRLS estimator provides also the tracking of non-stationary optimal reconciliation parameters. And since the proposed framework in the end is very basic and flexible, it will be easy, if needed, to add additional equality constraint, to generalize to multi-step ahead forecasts, because what we did was just on one step ahead forecast, and to generalize possibly to a distributed setting. So in the future, topic for future work could be to avoid privacy issues, to extend the estimators to the distributed setting, to implement specification, for example, in order to avoid or to minimize the number of alterations of forecasts. And then to implement some adaptivity of the forgetting factor and to possibly extend from our linear model to a non-linear model to account for conditional effects and so on. But this would, of course, mean that all the properties need to be validated again, to be confirmed and again. Finally, it would be also interesting, I think, to look at, quantify what is actually the improvement in decision-making value that is brought by ring reconciliation. That was it. Thank you for your attention, and I'm ready for your questions, if any.
Thank you very much, Chiara. And thanks for the timekeeping also. I can see you can ask your question in the Q&A. It has worked well before. It's in here with, oh yeah, so Patrick has a very interesting question. Chiara, did you try to perform clustering to select the hierarchy?
No.
How does one select a hierarchy?
So it's usually depending on the, I would say, on the decision-making problem. So it depends on where you need to have the forecasts, right? So for example, it would make sense to, for example, having a hierarchy where the regional, I mean, it's always depending on what the decision makers want. So if it's needed to make a be made a forecast at the node of a specific station, then you would use that you would use the child nodes belonging to that region to you would assign the child nodes of that region to that group. I don't know if this answers the question.
So, yeah, to maybe reformulate what you say, your point is that you say it's the actual physical layout and the decision-making problems that impose the hierarchy. It's not something that you try to define to maximize the improvement in forecast accuracy, for instance.
Yes, exactly. And that's also why, yeah, that's also why the randomization that we do in the Monte Carlo experiment is not actually, yeah, of course, it could be used in a portfolio problem for where they are geographically located, and then they are, geographical dispersed information, but not in a layer, physical layer.
The second part of Patrick's question was, do you think that weighted sums could be useful? And I guess by weighted sum, you mean a bottom-up approach where you simply just average by going upwards in your hierarchy. You see what I'm saying?
Yeah, if that is the question, that is actually a benchmark, not a benchmark, yes, it's an existing reconciliation method already, bottom up, but it proved to be quite biased. So depending on how many upper layers there are, there will be more bias in the upper levels in the forecast.
Yeah, and I guess that's the point of your work. You're trying to do better than that, right?
Yeah.
Yeah.
Exactly.
Okay, good. I have a quick points maybe to finish, because you mentioned that you get reconciliation by design as long as the measurements are additively consistent. But what if you use covariates like a weather forecast?
Yes. Well, but we will still need the measurements of the wind, power to perform reconciliation, to know what is the difference between what happened and what is the forecast of the wind power, because we were focusing on wind power. Is this, did I misunderstood the question?
No, no, what I meant is that here you use past measurements as covariates, right? And it is past measurements that need to be consistent to be sure. Okay, but so if you have extra covariates would just come from anywhere, right? Weather forecast, then you don't have this idea of consistency in your covariates. So then I guess
Yeah.
it just means that then you don't have this reconciliation by design without the equality constraint.
Yes, yeah, that's true.
Okay, good.
Yeah,
Just to be sure it's clarified.